All right, guys, let's take a look at section 5.2, exponential functions. And where the chapter is headed, we just talked about inverses, exponential functions and logarithms are inverses of each other. So eventually we'll work our way into logarithms and how to solve those types of equations. Well, today, an exponential function looks like f of x equals b to the x, some base to the x. You might have a number out in front that stretches or shrinks it, but in general, that b to the x. And that's for b's that are greater than or equal to 0. We're not taking a negative inside of there, okay? So here's some of the properties that we've learned in the past, and we'll just kind of reiterate those. If you're multiplying two exponents together with the same base, then you can add the exponents, you can add the power. So b to the m times b to the n is b to the m plus n, okay? A power, two numbers multiplied together raised to the same power, that power can be distributed in. So AB quantity to the n is a to the n times b to the n. The same works for division. If you have b to the m, or not, similar works. So up here when we multiplied, we added the powers. When we're dividing with the same base, we subtract b to the m minus n. A negative exponent just flips it. So instead of b to the negative n, it would be 1 over b to the n, it puts it in the bottom. A power to a power, you multiply exponents, so m times n. And if you have a fraction raised to a negative power, it flips the fraction and raises it to a positive power. Just, you guys can write that down, take a look at it, reference it. So, an example. Evaluate each exponential function at 2, -1, 1/2, and pi. Use a calculator for pi. So, this first function here, f of 2. Well, that's going to be 4 to the second power 16, okay? Not a big deal. F of -1 now, remember on the previous slide, if we raise it to a negative power, it flips it. So 4 to the -1 is like 4 to the first, which is 4, but flipped. It's going to be 1 over 4, okay? 1/2. Well, a 1/2 power, a rational power like that, involves radicals. So a 1/2 power is a square root. So the square root of 4 is 2. And then, of course, f of pi, we're really just going to grab our calculator. 4 to the pi power. The pi button is above that little caret button. I get 77.88. So to 5 decimal places, I guess. I'll put it up here. F of pi, I get 77.88023. Okay? Not a big deal. Okay, down here, g of 2. Well, if you have a fraction raised to a power, you can distribute that power to each of them. So 4 to the second is 16. And 9 to the second is 81, okay? G of -1 is going to flip it. So this is going to become 9/4. G of 1/2, again, that's the square root. So the square root of 4 is 2, and the square root of 9 is 3. G of pi, we're going to grab the calculator here, you guys. We're going to go 4/9 raised to the pi power, and to 5 decimal places, that's 0.07827. Those ones are just calculator problems. So these aren't too bad. I think you guys are going to have no problem with those. Okay? All right, graph it. So a couple things you need to know about an exponential function. It's always going to have a horizontal asymptote, and it's either going to grow, exponential growth, talking about the coronavirus, we've seen this quite a bit in the news. Exponential decay would be something that starts high and goes low. Typically your asymptote is going to be the x-axis unless we've shifted up or down. Okay, so we're just going to try some values. Go ahead and put this in your y equals and go to your table, and then we'll check and see what we get. Okay, so if you're following along and doing this on your calculator, 2 to the -3rd, you should get 1/8. 2 to the -2, you should get 1/4. 2 to the -1, you should get 1/2. 2 to the 0 is 1. 2 to the 1, 2 to the second, 2 to the third, okay? And really at this point, I just need to sketch those. So negative 3, 1/8 is really close, 1/4 isn't much higher, 1/2 isn't much higher than that, 0, 1, put in a 1, I get a 2, put in a 2, I get a 4, and put in a 3, and I get an 8 here. Okay? And again, that x-axis is an asymptote, so it should be getting close to it, but not touching it. Okay? And so, use the table in your calculator, use your resources, guys, to help you with this problem. All right. What about 1/2? If you take 1/2 to the negative 3, it flips it and goes 2 to the third. So now this is 8, 4, 2. Anything to the 0 power is 1. This would be 1/2, 1/4, 1/8. So it just kind of flips these around. At negative 3, I'm getting 8, and then 4, 2, 1, 1/2, etc. Here's an example of exponential decay. When that base on that exponent was bigger than 1, we were growing exponential growth, and when it was less than 1, we decayed. Okay? So in general, an exponential function here has these characteristics. It is 1-to-1, it's going to pass the horizontal line test. The domain is all real numbers, you can put in whatever you want. It's increasing or growing if that base is bigger than 1, like we had 2 to the x. It's decreasing if it's between 0 and 1, like 1/2 to the x. The y-intercept's going to be 0, 1, because when you put in something, raise something to the 0 power, you get 1. The range is 0 to infinity, not including the 0 typically, because that's where our asymptote is, okay? And that explains that last part there. So, graph that function using transformations. All right, so this plus 2 is moving everything up 2. So instead of our asymptote being the x-axis, our asymptote's going to be the line y equals 2. And that x minus 1 there is really just going to move everything to the right 1. After that, we're going to pick a few points, guys. So if I put in a 1, I get 0 here. 2 to the 0 is 1. 1 plus 2 is 3. So when I put in a 1, I get a 3. Okay? When I put in a 2, 2 minus 1 is 1. 2 to the 1 is 2, plus 2 is 4. So I'm getting 1 higher. If I put in a 3, I don't want to go too much higher here, though. I get 4 plus 2, I get 6. Okay? If I put in a 0, I get 1/2 plus 2, I get just above here. And we've got enough points then to help us sketch our graph. So it looks a lot like 2 to the x, you guys. That's kind of the parent function. But I've got a horizontal asymptote now moved up to 2 because we shifted up 2. And then we moved over the 1, over 1. So instead of having 0, 1, it's like 1, 1 at that point, above the asymptote. Okay? Clearly state the transformations. We translated right 1 and up 2. Okay, the number e. If you guys look at your calculators, you have an ln button on the left. Above it, it says e to the x. So we're going to use that value. If you put this into your y equals, if you want to experiment, go in y equals 1 plus 1 over x to the x, and then go to your table and make x be really big. So go by 1,000 or something. So have it be 1,000, 2,000, 3,000. As that approaches infinity, that's why we're making it get really big, e is about 2.718. Okay, and it goes on forever. This is an irrational number, so it doesn't just stop in 3 decimal places, but it goes on forever. So if you want to know about that, that's helpful. This will be really helpful when we do compounding continuously a couple sections from now. Use a calculator to evaluate e to the x for these. You guys, just practice on your calculator. This shouldn't be too bad. So the first one, I want to go e to the third. 6 decimal places, so 20.0855537. Okay? E to the first, 0.718281. Okay? Anything to the 0 power is 1, so that's easy enough. E to the 1/2, I get 1.648721. And just make sure, you don't have to try all these on your calculator, but just make sure that you can do it, that you can type it into your calculator, okay? Exponential equations and the uniqueness property. So if I've got an equation where I've got exponents on both sides and the bases are the same, then I can ignore the bases and just set the exponents equal to each other. So that's going to be my goal for the next couple problems here, okay? So for this first problem, if I want to solve this, I've got 3 to the 2x minus 1. Is there any way to rewrite 8 as a power of 3? Well, there is. It turns out 81, not 8, but 81, 81 is 3 to the 4th power. Now the bases are both the same, they're 3, so I can ignore those bases and say that 2x minus 1 has to equal 4. Add 1, I get 5 divided by 2, and x equals 5/2, okay? Not too bad. How about this second one here? So 1/6, if I flip that, that's a 6. So think of this as 6 to the negative 1, that's the same as 1/6, raised to the negative 3x minus 2. Equals 36 is 6 to the 2nd raised to the x plus 1, okay? Well, that being said, I do have the same bases now, and I'm going to go a power to a power, so I'm going to multiply these. So this is going to be 3x plus 2 equals 2x plus 2. Okay, so I subtract that, I get x equals 0. Does that sound right? Let me double check that one to make sure I did it right here. Yep. Okay, down here, this is e to the, when you have the same base and you're multiplying, you add the powers, e to the x plus 2. And when you're dividing, you subtract. So this is e to the 4 minus x plus 1. The bases are the same, you guys, so I'm going to ignore those bases again. And I'm going to say that x plus 2 has to equal, well, 4 minus 1 is 3, minus that x. Okay? Add x, and get 2x on this side. Subtract 2, and I get 1, so x equals 1/2. Okay? So that's what you're going to try to do. In each case, I got the bases to be the same. They were both 3, so I could ignore them and just set the exponents equal. They were both 6, I ignored them, set the exponents equal to each other, etc. Okay? All right, we're going to do one example, one word problem, then I think we're going to get you going here. So, as a part of their buyback program, a major electronics retailer estimates that electronic devices lose 20% of their value every 6 months. That's why this rate is 0.8 instead of 100%. The current buyback value can be modeled by this function, t over 6, because whenever you put a 6 in, it's going to reduce one time. So if I put a 6 in, I'll take 80% of it once. If I put a 12 in, it'll be 80% of it twice, etc. Where v sub 0 is the initial value, and v of t represents the value after t months. How long will it take a tablet that costs $625 new to depreciate to $256? Okay, so let's see what we have. V sub t was v sub 0 times 0.8 to the t over 6. Okay, so let's just remind ourselves here. We have 625 and 256. Okay, so 256 is the final value. 625 is where we started. Okay, so I'm going to divide both sides by 625. Now, the only way we've talked about solving these exponential equations is to get the bases to be the same, okay? So 256 over 625. That looks like a fraction that I can simplify. 256 over 625. Okay, let's see here. Let's do this, okay? On this side, 0.8 is 4/5. And is there any way to think of this as 4/5? Well, if I take 4 to the 4th power, I get 256. And if I take 5 to the 4th power, I get 625, which means this is really 4/5 raised to the 4th power. Okay? So, because I don't know anything about logarithms yet, this is kind of how I'm going to have to solve this. Okay? 4 to the 4th power is 256, and 5 to the 4th power is 625. And the reason I tried those is because I needed them to be the same as that one over there. Well, now I've got the bases the same, you guys, so I can ignore those and just set the exponents equal to each other. 4 equals t over 6, multiply by 4, and I get 24, remembering that t was months. It was every 6 months this happened, so 24 months would be 2 years if you were going to work that out. Okay? Well, I think we're going to stop there, you guys. And so, again, if you have questions, we have office hours 11 to 11:30 on Google Meet, so if you need to pop in, please do.